Today, we're going to pull back the curtain on the digital world and look at the absolute most fundamental building blocks of, well, everything. We're talking about logic gates. They are the tiny, microscopic switches that power every single thing you do on a screen.
I mean, it all really boils down to this one question, right? How does a machine that's just made of metal and silicon seem to think? Well, you'll be happy to know it's not magic. It's pure logic, just happening at speeds that are almost impossible to comprehend. So let's dive in.
All right, so to really get how computers decide anything, you have to look at their version of a brain cell. And these little components, these fundamental pieces, are called logic gates. At its heart, a logic gate is actually incredibly simple. It's just a tiny circuit. It takes in one or more electrical signals. Think of a 1 as on and a 0 as off, and then it spits out a single new signal based on a very specific rule. And when we say building blocks, we mean that literally. Every single processor, every chip inside your phone or your computer is packed with billions of these little gates, and each one is its own tiny decision maker. So if we're going to learn this language that computers speak, we have to start with the alphabet. And it turns out there are 3 foundational gates that pretty much everything else is built on. First up, we've got the AND gate. The best way to think about this one is like a really strict doorman at a club. To get in, you need to have your ticket and your ID. If you only have one, it's a no-go. You need both. And you can see that rule playing out right here in its truth table. Just look. The output is only a 1, or true, in that very last row. That's the only time when both input X and input Y are 1. Any other combo? You get a 0. Next, let's talk about the OR gate. Now, this is a much more chilled-out doorman. You can get into this club if you have your ticket or your ID. I mean, having both is great, sure, but just one of them is totally fine. And you can see that laid out perfectly here. The only possible way the output is 0 is if both inputs are 0. If there's a 1 on either of the inputs or both of them, the output is going to be a 1. Simple as that. And finally, we have the simplest gate of all, the NOT gate. This one is super straightforward. It doesn't combine anything. It does one job and one job only. It just flips whatever you give it. Yup, exactly as you see here. It takes just one input and spits out the exact opposite. We call it an inverter, and you'd be surprised how useful it is to just be able to reverse a signal. Okay, so we've got our basic alphabet, and, or, and not. But what if I told you that you could build every single word, every sentence, every idea using just 1 or 2 special letters? Well, that's where universal gates come into play. So check this out. A NAND gate is really just an AND gate followed by a NOT gate. And a NOR gate, you guessed it, an OR followed by a NOT. The reason they're called universal is because you can create any other logic function, and or anything, just by combining these. That versatility, plus the fact they're really efficient to make, makes them the true workhorses of circuit design. Okay, so far we've been talking about these simple true or false, yes or no decisions. But this is where it all comes together. How do these simple little rules let a computer do something as complex as math? This is the big question, isn't it? We've got these gates that can say yes or no. How in the world do we get them to say 2 or 5? The answer, it turns out, is in combining them in a really clever way. To do math, we need one more special tool in our toolbox, the exclusive OR gate, or XOR for short. Now, unlike our regular OR gate, this one is picky. It's only true if the inputs are different, so one or the other, but not both. And this is the aha moment. This is amazing. On the left, you see the truth table for that XOR gate. On the right, you see the rules for adding 2 binary digits. Look at that sum column. 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. The sum column and the XOR output, they are identical. But hold on, what about that carry the 1? Well, check this out. If we put the truth table for a basic AND gate right next to the carry column, they're exactly the same. You only carry a 1 when both of the input bits are 1. It's a perfect match. So here's the punchline. By wiring an XOR gate and an AND gate together, just like this, we've built a circuit called a half adder. It can take 2 bits, calculate their sum with the XOR, and figure out the carry with the AND. We have just taught a piece of silicon how to do basic math. That's incredible, right? But it's still just adding 2 single bits. how do we go from that tiny operation to calculating, a huge spreadsheet or rendering a video game? Well, we scale it up, way up.
So the next step is to combine two of those half adders we just made. What we get is something called a full adder. And what makes this so powerful is that it can add 3 bits at once, our 2 regular inputs plus a carry in bit from a previous addition. That right there is the key to adding numbers that are bigger than 1.
From there, the idea is just beautiful in its simplicity. You just chain these full adders together in a line, one for each bit in the numbers you want to add. As you can see here, the carry out from the first adder becomes the carry in for the next one, and so on down the line. This ripple effect is how computers can add numbers of pretty much any size.
And that's really how it's all done. You take those simple logic rules, and you just repeat them and combine them on a scale that is almost impossible to imagine. A modern processor has over 15 billion transistors, with each one acting as a part of a gate, performing these basic logical steps trillions of times every second. So, from a simple AND gate to a complex calculation, it all comes back to these fundamental, almost simple rules of logic. It really makes you wonder, with these powerful, basic building blocks, what are we going to design tomorrow?